So the next step was they went to a little bit larger amperage, but still not enough for today's vehicle. But what they did on this one is they changed that I wire to F, which means it monitors it. So now we can check to see what the alternator load is. And when I say we, the PCM can look at the load of the alternator and determine whether it needs to filter or turn down the voltage on it when it comes to a stop. So the PCM knows if the car is moving or not. It looks at the vehicle speed sensor. It starts to come to a stop. It lowers the voltage on the alternator and then adjusts the idle while it adds the loads back in. And that's called load response control. So we don't have that idle stumble anymore when you come to a stop. Uses that for a variable duty cycle on that F terminal. And here's how that works. See the PLFS? Again, if you are concerned with which one it is, because the case will say I and F, so if you really want to know which one it is, you can look that part number up and pull that schematic of the actual plug-in right off of RemyAutoparts.com. So on this one, the way it works is you turn the key on, and the PCM tells the instrument panel cluster, or the IPC, to turn the light on. Once it starts to charge, the PCM will then tell the bulb to turn off. But as it's charging, you see what it's doing there. It's sending back a signal on the monitor line, or the F terminal, indicating the alternator load, so that the PCM knows that what the load of the alternator is, whether or not to turn it down when it comes to a stop. Make sense? So the benefits of the system we're getting ready to talk about, which is the RVC system, regulated voltage control, are that we're going to increase the life of the battery. The way we do that is that we're keeping that battery at 85% state of charge or higher. Because the PCM is constantly monitoring the state of charge of the battery and constantly monitoring the amperage going in and out of the battery, so it knows when to reduce the voltage on the alternator so that we can put that horsepower back down the crankshaft, and when to kick the voltage back up. As you'll see here in a minute, it's great for gas mileage, but if your customer still has a gauge in the car, which most of them don't today, the first thing you do is you put an alternator on their car, and they go out and they drive it, they call you up and say, hey, something's wrong with this alternator you put on because now I'm having intermittent problems with it. I'm driving down the highway and I see it drop off to 12 volts. Well, they've owned it since it was new and they never saw it. Why are they watching it now? Because they've got broke down somewhere and you guys put an alternator on. But it's completely normal for this system to do that. It's going to have improved fuel economy and also improved performance, because we're going to take that horsepower and put it back down the crankshaft where it's needed. Improved idle stability, because it has that load response control I was talking about. When the alternator is loaded, it reduces the voltage when it comes to a stop, feathers the loads back in while it's adjusting the idle to compensate, so your customer sees a seamless idle. Here's the primary components. There are other components that deal with it, and as you'll see, but these are the primary ones. You got your alternator with your solid state voltage regulator. You have your battery current sensor. You have your BCM, your body control module, and then your powertrain control module, or your PCM, involved in this system. So like I said earlier, this is now a closed loop system. It's being told what to do. Even though the regulator's regulating the voltage, it's being told what voltage to regulate it to. Here's a little bit about that voltage regulator. And again, you see that B circuit up there. That's what that means, is that whenever this thing applies voltage to the rotor, it's applying battery voltage. It's not applying a ground. But this has three features on here that I want to talk about. Load response control, I want to talk about soft start, and I want to talk about fault logic. Now, fault logic is a little bit tricky because as a technician, if I went out to a car and it was charging and the battery light's on, what the heck? I unplugged the voltage regulator and it still charges. All the newer cars, 2005 and above, GM started this in 2005, but most of the manufacturers, some of them started before, depending on the model, but most manufacturers after 2005 and above, you can unplug that and it'll charge us to help get the customer home. Here's the microprocessor that's inside of that voltage regulator, and if you see, it's the size of a penny. It's got wire a third the size of human hair that's made out of gold, and then it's got up to 30,000 transistors in it. It's that small. But you know why they use gold in the wire? Is it? I was told it's for corrosion. I'm just curious. Just curious what the answer would be. Huh? It is a very good conductor. Copper is the best conductor, but it has corrosive properties to it. So gold is just as good, but it doesn't corrode, and that's why they use gold. Good answer. So here's what's inside of that chip, and it's kind of scary when you look at that. My boss could sit around and tell you what each one of these was. I probably could too if I looked at it long enough, but we only care about what? The two prongs that stick out of that alternator. That's the only ones we can even get to. Agree? L and F. That's the two prongs that you're going to see sticking out of that regulator, the two connectors. The L is the on command, and your F is your return signal, and that's your monitor signal. Here's a load response control. This is the first benefit, the one I just talked about a second ago, where if we could have left the rest of the screen on there, you'd see that it was up in this range as far as what the alternator was doing as far as load. But as soon as that car comes to a stop, it drops it down, drops the voltage down, so it reduces the magnetic force. And as you can see, it starts feathering it back in, but while it was doing that, it's adjusting the idle. So it brings it right back up to the same load that it was at. Customer doesn't feel a thing. Soft start's the next feature of this regulator. Soft start's pretty cool because what happens is this alternator does not turn on for 10 seconds after you start it. You think, why would they do that? Well, think about this for a second. If you can unload that alternator, that starter doesn't have to pull that alternator and the belt drive, loaded down belt drive, with the engine. If you can spin it quicker, you're going to start it faster. Less wear and tear on the alternator, less wear and tear on the belt drive, less wear and tear on the starter, and less energy used out of the battery that we have to put back in. So the alternator doesn't have to put as much back into the battery because it starts quicker. So that's soft start. The other thing to remember though is when we're doing diagnostic is that immediately when you start it, you're not going to see a signal there for about 10 seconds. So here's that fault logic I was talking about. And this thing will pass, you can unplug the regulator and it will pass every single test. Because once the regulator, that microprocessor I showed you, one of the size of a penny, once it sees that there's no communication or there's an issue with communication, it will immediately self-excite. You'll get a battery light on because your battery light for this system is your check engine light. You're not going to see a check engine light, but if that battery light's on, you're going to have codes. Because let me explain something. With that L terminal system I showed you a second ago, this is how this goes down. Your customer's driving along and his battery light comes on, his or hers. She brings it to you, he brings it to you. You look at the car, it's not charging, the battery light's on. You do your tests, you change the alternator out, and the battery light goes back off, boom, it's fixed. These newer systems, they come in with the battery light on, you're thinking, okay, put an alternator in it because of the mindset of the past. You put an alternator in it, boom, the battery light's still on because you've got code stored. It may be a communication, which I'll show you when we get to diagnostics. But it's a lot different than the alternators of the past. Here's your Hall effects sensor or your battery current sensor. It is a Gauss meter, a amp clamp. What it does is measures current going in and out of the battery. A couple things here. It's measuring current going in and out. So when we change out cables, let's make sure that nobody puts it on backwards. Because unlike us where we see a negative and a positive, we just flip the amp clamp over and we realize, hey, now it's normal. On this particular case, the computer knows positive and negative, wants to see it charge and discharge. So it pops a code if you get it on there backwards. And if you look at this, it's got 3 wires going to it. One of them is going to be your 5-volt reference. One's going to be your pulse width modulated signal, which is a variable duty cycle at 128 hertz. And then you're going to have a sensor ground as well. So the 3 wires come out of here. If you see an issue with it or you get a powertrain code, as you'll see when we go through the diagnostics also, 85% of the time on this thing, you just unplug it and clean off the plug and put it back in. This can be mounted on either side, but again, if it's on there, you don't want to flip it around backwards. One of the things that this does is the PCM is constantly monitoring that battery for state of charge, and it's watching the current flow coming out. So when it sees that the state of charge is 100% or 12.6, it will reduce the voltage on the alternator. Because the way the alternator charges the battery is, it has to be a higher pressure, pressure being voltage, has to be a higher pressure than the battery by 1.3 volts to push current towards the battery. So what it does is it drops the voltage down so the pressure is the same, so there's no current flow going on those lines. But at the same time, as soon as the PCM does that, it watches, there's still amperage coming out of that alternator, it's running the system, but it's just at a lower voltage. It watches the current coming out of that battery and determines by what the state of charge was when it turned off, the state of health of the battery, and how much current's coming out, when to kick that alternator back up to a charge state. So that's why it's important to make sure that you put that on there the right way. The other part of that is that when the PCM goes to sleep, it says, I went to sleep and I had 12.66 on my battery, which is 100% state of charge. I've been asleep this long. I know the regular drain for the vehicle is this amount. It does a calculation and says, my state of charge should be here. It wakes up and the state of charge is down here. It'll pop on a code that says parasitic drain, because something's being left on and draining that battery, or the battery's gone bad. Other point to this too is you see that GND on the bracket for the alternator. You're starting to see that more and more on the newer cars. And it's not like the BMWs where they put a remote jump post. The reason they do this is because if you're jump starting a vehicle with a jumper pack or charging a vehicle, you want to put your ground, or just get in the habit of putting your ground over there on the block. The reason being is because it's constantly monitoring that amperage going through that cable. You want to make sure that the PCM can see that current flow going through there. The BCM is the next piece of the puzzle. This is body control module. What it does is it takes all that information, meaning the information from the battery current sensor as far as how much current flow is in and out of the battery, in or out of the battery, and looks at the voltage sense lines to see what the state of charge of the battery is, and then it looks at the intake air temperature sensor to see what the temperature is under the hood, so they can overcome any heat resistance output losses. It does a calculation and then sends the suggested voltage set point or required voltage set point to the PCM, which is the next piece of the puzzle. When you first start the vehicle, it's looking for under hood temperature right there at that intake air temperature to kind of determine what it's going to be. Before any airflow occurs. Exactly. And then after that occurs, it still uses that, but it has an algorithm already included into the PCM that will tell it if it's this temperature, this is how much it is under the hood. So that's how it uses that. But it receives that BCM over the CAN line. And now the BCM uses a local a local area network, meaning that the BCM looks at the other sensors to determine something, but then it sends it on a controller area network, which is just one wire going to PCM, so that it can reduce the amount of copper for one reason, but also it's also expensive to have that much copper. The PCM receives the desired set point from the BCM, body control module, over the CAN line. The PCM then sends 128 hertz signal at 5 volts, variable duty cycle, over that L terminal to tell that alternator's microprocessor to turn on. Once it starts up, starts charging, the F terminal is the terminal that the regulator will send a variable duty cycle at 400 hertz, 12 volt signal back to the PCM to tell it what the alternator load is. The PCM will also monitor that F terminal and the L terminal for any faults, and it communicates the driving conditions to the BCM. Because remember how the load response control works? We're coming to a stop, look at the vehicle speed sensor, that kind of information. Where's the throttle position sensor? As you'll see in a couple slides away, the throttle position sensor actually will kick the voltage back up if you're in fuel economy mode, back up to charge mode. So in order to understand what we're going to talk about, let's talk about frequency. Frequency just means how many times a second something's happening. Well, in this case, it's in hertz. So frequency is measured in hertz. 60 times a second in this room is going positive and negative on that AC waveform. But we're going to look at a DC waveform, and what we're looking at is they're going to use this for a square waveform for communications. So this is a really low current communication signal. So if you were to ground this, it would just go to 0. It wouldn't melt the wire. When you look at that, this is one segment to here, 2 segments, 3 segments, and then 4 segments. This is your on time, and this is your off time. And that's how it would look on a scope. So that is on and off about 4 times a second, so that would be about 4 hertz. But what we're looking at is 128 hertz going to command the alternator to turn on, and 400 hertz on the return line to monitor the performance of the alternator. So what's duty cycle? You notice that pretty much looks the same as that last slide, right? Because it's just frequency, is just how many times it's happening. But what we want to know is what's duty cycle? Duty cycle is the comparison of on to off time in a percentage. That top slide right there is on about, would you say, half the time? And off half the time? So what would that be in a percentage? 50%. Now your digital volt ohm meter, your DVOM, a lot of them, if you've ever seen it, you'll look over there and it says RMS on it. Anybody ever see that? It means root mean squared. That means this is an averaging meter. So instead, if I set 12 volts in on that side, and it's at a 50% duty cycle, instead of saying 12, 0, 12, 0, just flashing 128 times a second, what it's going to do is it's going to look at what the percentage of on time is and take it times the voltage going in. But what it does is averages it on, off, how many zeros, how many 12s, adds it all together, divided by how many times that happened, boom, and gives you a number. But it's much easier to realize that 50% of 12 volts, what am I going to see on my meter? 6 volts. And that's how that works, because it's only on half the time. You're only going to see half the voltage. This would be about 10% of the time on, so I'd see 1.2 volts. That's going to be on about 90% of the time, so I'm going to see 10.8.